First, I'd like to thank Jeff, Andrew, Daniele, and Sarah for organizing this amazing conference. This is my first time at Chapman, and I enjoy it immensely. Obviously, I'm dedicating this talk to Yakir, and actually Yakir's many contributions to science. So let's see how this goes. For those of you who don't know, I was a master's student and then a PhD student of Yakir and Lev later. So it's a great honor for me to be here and respect Yakir. Just a few words about myself and my group in Israel. We are called From Quantum Foundations to Quantum Technology. And this reflects my own trajectory. We started with fundamental quantum science, working on entanglement and non-locality, weak values, weak measurements, quantum time, and recently also information-based approaches to quantum gravity. But it's this era that forces us to work also towards the technological aspects of this basic science. So we are also doing some quantum computation, communication, simulation, sensing. Large part of it is tightly inspired by Yakir's idea. And I really love it because I see how Yakir's fundamental idea affect new technologies, and there's also a unique opportunity to test many of Yakir's ideas with novel setups. So this is what we do. And now, this is a non-exhaustive list of some gifts that Yakir has given us. New topological effects, the Aronov-Bohm, Aronov-Kasher, Aronov-Anandan. In this review paper, we surveyed them all, connecting them with the geometric phase, and also have some summary of all these phases and their unique properties. Yakir has also made great contributions to quantum measurement theory. These von Neumann-Hamiltonians that were mentioned, compensating forces, what can be measured, what cannot be measured, and how quickly. So if, for instance, we want to measure the energy of the system, this was one of Yakir's first papers. Is there a time-energy uncertainty relation? Which is also a funny story about his PhD with spirals. Yakir, I don't know if you know, has also explored, I think, the first experimental demonstration of the EPR paradox. 7 years before John Bell, Yakir and Bohm suggested an experiment based on the Compton scattering. They took actual data to test the EPR paradox. At the time, there wasn't a test like a Bell test for a local hidden variable theory, but the quantum part with spins, not with continuous variables, was already examined there. Yakir slightly later suggested the notions of dynamical non-locality with modular operators. These are the works that he did already in the 60s. Much later, the development of quantum walks, which are now important tools in quantum simulation and computation. The ABL formula that Yakir mentioned, weak measurements, weak values, protective measurements mentioned by Lev. Statement, obviously, of many new quantum paradoxes and the resolution of others. The notion of super oscillations, which was majorly discussed yesterday and also developed by Berry. Quantum frames of reference, super selection rules, especially charge super selection rules, and actually many more. So I think that this is an amazing list, and there are many other somewhat forgotten papers which I'm sure people will later on discover. So this is very inspiring for me, at least. But actually, Yakir has given us many other gifts, has given the world many other gifts. So here I hope to not get too emotional, but of course, when we speak about someone's gifts to the world, these are his children and grandchildren, but also the scientific children. Many of them are sitting here. Many fortunate collaborators and other people whom Yakir inspired and advised. I saw many of them in action, receiving Yakir's advice. But not only with people, the ideas sometimes remain even longer. So I hope I do justice with Yakir when I'm saying that Yakir taught us how to do theoretical physics. First, the notion of paradox. We start with an open problem, we start with a conflict, and through this conflict, we learn new things about science. I think that this is a recurring theme in Yakir's thought. Another one is that we should always start with the physical intuition. Only when we have the right physical intuition, we can do the math, but the math is secondary to our deeper understanding. The questions, as always, are more interesting and more important than the specific answers. And if I may say, we can also learn from Yakir how to live freely, that is with a free will, with a genuine responsibility for our faith, which is made even stronger once we realize that there is just one world, not many, many worlds, in which we can split our choices. So for Yakir, I know that this is important, the moral aspects of a single universe. Yakir has also taught us to be bold in our thinking and also optimistic. I know that Yakir is really optimistic, even these days. And Yakir has remained very curious, very passionate about science. So I think we can take all these from Yakir with much gratitude. So I cannot talk about all these, although I think we did together research on most of the topics above. So I got the advice to choose what excites me the most. So first, I'd like to talk about some very recent laboratory experiments which test weak values and weak measurements. And then I want to talk about a theme that Yakir likes, the reason that God plays dice. Still related to these new developments in quantum measurements, I'll speak about quantum computation and how we realize weak measurements through quantum circuits. And finally, and actually the main scientific part will be about clocks, following Andrew and David's talks, and also time-energy uncertainty relations studied here by Serge and Sandu. So, okay, this is a long list. Weak measurements. So, weak measurements have been demonstrated numerous times. And I wonder whether those days in Kaplan building with Dave Albert and Lev, you imagine that they will be so influential and will be demonstrated so many times in so diverse systems. This is our experiment when we realized weak measurements with trapped ions. I think that this is the second demonstration, or maybe the third demonstration of weak measurements with massive particles. We coupled the intrinsic electronic state, actually the spin, to the axial vibrational motion. And when the vibrational motion was small enough, compared to the uncertainty, we got weak measurements with trapped ions. But we also realized weak measurements with free electrons. And this is related to what Yakir said yesterday. A charged particle creates a weak electric field, weak compared to the electromagnetic vacuum. So this is what we used in order to demonstrate weak measurements with electrons as well. But I'm most excited about this recent preprint with the Genovese group. I'm excited because we worked on this for about 10 years. And finally, we were able to realize this schematic setup. We had an entangled pair of photons, and then we ran a Bell test on each and every pair. So we had two entangled photons. Now each photon was measured in both bases. Usually Alice and Bob in a Bell test, they have to make a choice. Either they measure this or this. In this experiment, Alice made both her measurements, Bob made both his measurements, and on each and every pair, they evaluated the Bell parameter. Not only that, because these were weak measurements, entanglement was barely destroyed. So they achieved the Bell parameter and maintained entanglement of the two photons. Of course, the details, the experimental details are more complex, but I think that the results are interesting. So what we can see on the right is a very sharp peak at the 2 square root 2, the maximal violation of the Bell inequality. But at the same time, on the left, we can see that the fidelity to remain in a maximally entangled state remained very, very high. It's close to 100% of maintaining the initial state. We also calculated the purity, and the purity was also close to 1.
Can you explain what's on the x-axis and what's on the y-axis?
Yes. So left or right panels? Both, okay. So the right, on the right, what you see is a histogram. And because we measured the Bell parameter S on each and every pair, we gathered the results. So this is a histogram. For each time we measure 2 square root of 2, we put here just another line. So eventually we get a sharp peak close to the maximal violation, okay? And surely we get some other results as well because the measurement is weak. But statistically, the most common value is the 2 square root of 2, the maximal violation, okay? So this is on the right. On the left, this is sort of a tomography of the bipartite state. So in the basis of HH, HV, VH, and VV, for the two polarizations of the two photons, we can see that the state is in the maximally entangled singlet state. And the fidelity after the weak measurements remained pretty close to 1. So in some sense, we ate the cake and left it too. We had the cake and left it too. So this is one exciting experiment. Another one with Ryo Okamoto from Kyoto came to test Yakir's paradox of the disappearing and reappearing particle. Yakir mentioned yesterday the 3-box paradox. And we have a version with Avshalom where there is some tunneling between the boxes, so the particle can move from one to the other. And when we did this optical experiment, we saw that indeed there is a +1 weak values for box A and box C, but there's also a negative weak value for box B. Later on in time, because of the tunneling, the negative weak value changes box, and the positive weak value changes the box. But what's important is the sum. The sum of the two weak values is 0 here and there, and therefore there's a moment in time in which these two boxes, which previously contained a particle, are now empty. So this is a demonstration of the disappearance of the particle, but it's a time-dependent experiment, so it also reappeared later. Also interesting here are the sequential weak values. So we calculated the temporal correlations, which show that even here, in this moment where we think that both boxes are empty, there is something left in the form of temporal correlations. So these are some nice experiments, I think, but personally, the one here is the most important for me, because it doesn't test Yakir's prediction, it tests my prediction with Avishai Karmi. But actually, it also starts from Yakir, because I think it was the late 80s where Yakir had a claim that quantum mechanics can be non-local as it is without violating causality only because of uncertainty, right?
Yeah.
So I think that in this inequality at the bottom, we see this. We see B. B is the Bell parameter or the CHSH parameter. It can be as high as 2 square root of 2. But it doesn't always reach 2 square root of 2. It can reach the value 2 square root of 2 if and only if the local operators on Alice's side or on Bob's side for this matter are completely uncertain. It's only when Alice's measurements do not provide any information about each other that we are able to reach the maximal bound on non-local correlations. And I think that this is important because this also shows the importance of weak measurements. There are some models called PR boxes, Popescu-Rohrlich boxes. Happy that Sandro is not here. In which you don't have access to this part. And there's a very good reason you don't have access to this part in Popescu-Rohrlich boxes, because this part in Alice's lab depends on Bob's choices. You can show that if you had access to this variable in Popescu-Rohrlich boxes, then you would violate causality. This is what we found. Now, you can ask, what is the empirical significance of this value? A0 and A1 are Hermitian operators. So A0, A1 is non-Hermitian. You could think that I'm not able to measure it, right? But we can measure it using weak measurements. And this is what we did in that experiment. We measured A0, A1, the local correlation. We measured the Bell CHSH parameter. And we saw that this inequality holds. If you want maximal violations of the Bell inequality, if you want to have maximal non-locality, you must have maximal uncertainty. Otherwise, you won't be able to be violating maximally the inequality, and actually you won't be able to be quantum at all. So this reflects on the major importance of uncertainty in quantum mechanics. So this is to say that, as already claimed by Yakir many years ago, God does play dice, and Yakir postulates that God plays dice in order to save free will. A different way to phrase this sentence is to say that God plays dice to save causality, right? So this is just a side comment, but I believe that when you start with uncertainty as a postulate, you can derive anything. So here I showed you that once you have uncertainty, you can derive non-locality. And actually, when you start with these uncertainty relations, we have shown that you get something which looks like the Tserelson bound on quantum correlations. But we can also show that it leads to contextuality, a milder version of quantumness. It obviously leads to quantum equations of motion, right? Because the Heisenberg equation depends on the commutator. It leads obviously to quantization. It leads to any quantum phenomena as far as I know. So if you are aware of a quantum phenomenon that cannot be explained by quantum uncertainty, please let me know. I haven't found one yet. Okay, so Yakir knew how to prove this in the context of dynamical non-locality. He showed that whenever you have two wave packets, I don't have the picture, but Yakir showed you this picture many times. You all remember the picture of two wave packets with a relative phase and the modular operator e to the power of IPL. And this operator obeys non-local equations of motion. How can this be? How can the dynamics depend on two remote points in space? Yakir showed that this immediately entails maximal uncertainty in the phase. So here too we see that God plays dice in order to allow non-locality without violations of causality. This was shown in this paper. I will show later, if I have time, that you can show the same for dynamical non-locality in time. So if you have some equation of motion which depends on two remote points in time, then again you must have complete uncertainty regarding the phase. So this is the picture of the interrelations between relativistic causality, quantum non-locality, and quantum uncertainty. We explored these relations in the paper below. We means Avishai Karmi, a very talented collaborator, and I. And I think I said enough about that, unless you are interested in some more technical details. I know that lunch is approaching quickly, so I think I can be a bit quick about that. Let me just reiterate once more the bottom line. In all Bell experiments, we used to think about 4 pairs of correlations. Alice can choose either A0 or A1. Bob can choose either B0 or B1. And then we compose 4 correlators, C00, C10, C01, C11, and there's a bound. What does this bound depend on? We found that this bound depends on the local correlations between the operators in their own labs. So the extent of violations of Bell inequalities depends on the uncertainty within Alice's lab and within Bob's lab. And this is not a qualitative claim alone. We actually have quantitative expressions. So if we have a matrix of correlations on the right here, you don't see my mouse. If you have a matrix of correlations on the right, these correlations are the Pearson correlations. Then they are bounded from above by what? They are bounded from above by local correlations. Local correlations determine the extent of non-local correlations. This is because of quantum uncertainty. Quantum uncertainty is the enabler. It enables virtually anything that we see in the quantum world, if I'm not wrong. Maybe I'm wrong. Yes?
Try to understand those
Please.
inequalities up there.
Sure.
So what constrains what?
Maybe I'll show you a simpler version. It won't look simpler, but it is, okay? I promise. Okay. let's look, for instance, about this inequality. B is the CHSH parameter, okay? In quantum mechanics, it's bounded by 2 square root of 2. This is the Tserelson bound, okay? This is the left-hand side. Now you are asking, what is the right-hand side? What is the bound? It's not only 2 square root of 2. 2 square root of 2 is a point, but you can have an entire set of correlations. What bounds this set of correlations? What bounds this set of correlations are expressions which depend on those etas. Eta is the local correlation in Alice's lab. If Alice makes 2 very correlated measurements, if her choices are correlated, then she won't see violation of the Bell inequality. But if Alice's measurements here are completely uncorrelated, like the outcomes of sigma x and sigma z, right? These are mutually unbiased. If you have the result of one, it gives you nothing to know about the other. This is what you need in order to maximally violate the CHSH inequality or any other bound on non-local correlations. So the right-hand side quantifies local correlations, and when there are local correlations, there won't be non-local correlations. In order to have strong non-local correlations, you must minimize the local correlations.
So say in order to have B large,
yes,
you need to have the real part of eta small or large?
you need to have it 0. Eta needs to specify 0 correlation between Alice's outcomes.
So if the real part of eta is 1, then
If it's 1, you return to the classical bound, to the Bell bound. Classically, you can do only better as square root 2 times square root 2. So you get 2. This is the inequality by CHSH. But if you want to get quantum, you must have measurements which are incompatible. You must have intrinsic uncertainty in Alice's measurements and in Bob's measurements. Otherwise, you won't be able to violate a Bell inequality. Oh, sorry. I got correlated to the chair. Let's see. So this is the story. It was tested also by the Karimi lab in Ottawa. Okay, this was a comment to Paul, but Paul is not here, so never mind. Another thing that people do today with weak measurements, they measure them using quantum computers. So in this work with the group of Ernesto Galvao, we first put weak values in a larger context. The larger context has in it a notion which not many people know about. It's called Bargman invariance. What is a Bargman invariant? A Bargman invariant is a variable which remains unchanged when you perform some invertible or, in quantum mechanics, unitary evolution on the entire system. So the simple Bargman invariant is the scalar product. If you have 2 states and each of them is evolved unitarily the same way, then this remains invariant. The third order Bargman invariant is this one, right? These are cyclic structures with inner products, which can be defined for pure states, but also for mixed states. I think that Justin knows them well because he also worked on the Kirkwood-Dirac quasi-distribution, which makes use of them. Bargman invariants are interesting because they quantify something we call set coherence. If you have a set of states, then you can use these creatures to quantify the global coherence of all these states together. And you can also use the negativity or imaginarity of Bergman invariance to witness quantumness and even to show advantages in metrology. This is what Ephraim Steinberg did. So, yes, this is about Bergman invariant and the claim that the weak value can be rewritten as a ratio of two Bergman invariants, the third order and the second order. And this is helpful because we know how to compute these invariants on a quantum computer. And actually, not only weak values, we can use Bergman invariants to create the Kirkwood-Dirac-Vazik probability distribution, the quantum Fisher information, again which Steinberg used, the popular out-of-time ordered correlator, and some other functions of the spectra of the states. And these are the circuits. So much in the spirit of this era, we have taken weak values into the realm of quantum computation and showed how we can construct simple quantum circuits which enable to calculate weak values without post-selection and without weak coupling, and just compute them on a quantum circuit. So this is just another recent result I wanted to speak about. And now the question is how much time I have. I still have some time, right? Yeah? Okay. So let's use the water provided by Jeff. So now I'll try to be a bit more didactic. I'll try to make the story shorter and fuller. This story is based on these publications. You can see here Yakir, of course. So first, some background. There's a problem called the problem of time. The problem of time arises as a conflict between the role of time in quantum theory and in general relativity. In quantum mechanics, we often treat time as a background parameter, right? It's just a parameter we insert into the Schrödinger equation or the Heisenberg equation. It's not a dynamical variable, right? It's not an observable. Also, time in quantum mechanics is universal, or apparently universal for all observables, and it's absolute. In contrast, within general relativity, time becomes dimension in space-time. It can be affected by mass and energy. So it's dynamical and it's relative. Different observers see different times. The problem of time becomes most apparent within the Wheeler-DeWitt equation in quantum gravity. This equation looks like a time-independent Schrödinger equation. And if you want, you can think about it this way. But actually, it embeds some Hamiltonian constraints into general relativity within canonical quantization of the theory. So this equation is problematic because time is not there. This is completely static. So if we continue from what Paul said yesterday, we can have some wave function of the universe, but this wave function of the universe is completely static. We don't have time. This is the problem of time. Okay? Now, this problem, as I will show next, may be connected to the problem of time operator in quantum mechanics. So as we discussed, time is typically understood as a parameter. Why is that? Mostly because of Pauli. Pauli argued that if time is treated as a quantum observable so that it obeys this commutation relation with the Hamiltonian, then the Hamiltonian must be unbounded from below. And this is bad, because this signals instability. If the Hamiltonian doesn't have a lower bound, then it always wants to go lower and lower and lower. This, by the way, appears also in Yakir's book with Daniel Rohrlich. So what to do, or how to address both these questions, the problem of time in quantum gravity and the problem of defining a time operator in quantum mechanics. There is a proposal by Page and Wouters, which actually appeared also in a paper by Yakir and Tirza Kaufer, how to use an external clock and make it entangled with the system such that a clock reading projects the system onto some definite time state. So let's see the Page and Wouters timeless framework. The starting point is the Wheeler-DeWitt equation. So we have some h acting on a double ket wave function. It's a double ket because it lives in a larger space containing both the clock and the system of interest. Now, what we have for the Hamiltonian, the total Hamiltonian is the Hamiltonian of the clock, the Hamiltonian of the rest of the system, and potentially some interaction term. Now, if for simplicity we treat the Hamiltonian of a clock as, let's say, p, just the momentum of a free particle on a line, and we use this rule for time, then we can replace HA by IH bar d to dta, and we regain some notion of time. So we use some external Hamiltonian HA, here with a very simple form, to reobtain the Schrödinger equation. So here once more we have dynamics. Out of the absence of time, we get some effective notion of time and an effective equation of motion. The effective Hamiltonian now depends on the system, but on the interaction with the clock. This is the proposal of Page and Wouters. So we have this large state psi double ket, and we always project it onto some plane with a definite time eigenstate. The time eigenstate defined here. Okay? This is not new. Very, very old actually, 40 years. But now we try to employ it to study two things. We wanted to study time-energy uncertainty relations, much in the spirit of Yakir's exploration 60 years ago, maybe. And also to study the relative perception of time using two different clock systems. And this was surprising. So when we have two clocks, now we are making things a bit more complex. When we have two clocks, an inner clock within the system R and some external clock A, we can ask about the dynamics from the perspective of clock A and about the dynamics from the perspective of clock B. And these are not exactly the same because the clock in system B may have, for instance, a large uncertainty. So things here becomes not trivial. This is just to recap. There's no time operator canonically conjugate to the Hamiltonian of the system. There is a time operator of the clock, of a subsystem, and it has its own Hamiltonian to which it's conjugate. This time operator obeys what we call the covariance rule for time evolution. So it evolves systems in time using this equation. And the wave function obeys this rule. So this is the integral version of the projection I showed before. Now there are many generalizations which I won't talk about. But anyway, this is the story. So now time, energy, uncertainty relations. And this is, again, a historical story. At the beginning, 1931, two prominent physicists, Landau and Peierls, believed that there are time, energy, uncertainty relations. Or in other words, you can't measure the energy of the system as fast as you want if you wish to achieve some good accuracy. But then, remarkably, Yakir, as a PhD student, has shown together with Bohm that this is not quite the case. Landau and Peierls didn't have the most general measurement formalism. They didn't consider the measurement procedure carefully enough, but when you really do the measurement correctly, you see that there's no lower bound on the duration. There is no lower bound on the duration as long as the Hamiltonian is known. Yakir showed that later with Serge and Sandu. And then there are other subtleties, such as who performs the energy measurement. Do you measure the energy using an external system with its own clock, or you use the internal clock, and this governs the dynamics? So these are important subtleties which can be summarized in this table. So this is what we knew about 2 years ago. 2 years ago, we knew that for some cases there are time-energy uncertainty relations, and for some cases there are no time-energy uncertainty relations, but there are some unknown cases. I'm skipping now the case of an unknown Hamiltonian, and I focus on known Hamiltonians. So this is what we know. This is what we know, and this is what we don't know, and this is what we want to find out now. If you carry out the energy measurement of a system, and the time comes from an internal clock, is there a time-energy uncertainty relation? And if you make the measurement of the energy using an external clock, with whether there is a time-energy uncertainty relation. These are the questions that we had. I must say at this point, because it's already late, that all this would not have been possible without Ismael Lucas de Paiva. He was a PhD student here. Yakir supervised him with Jeff. He's a very, very talented young researcher, now at Sandu's group. Right. Serge, you were there. Okay. So let's answer the question. This is the scenario. We have system R, whose energy we want to find, and we have some measurement device E, which can get its time from an external clock A or internal clock B. Now let's see what's happening. Let's start with the case where the energy measurement is carried out by an external system. That is, the clock is coupled to the measurement device. The measurement device gets its time from an external clock rather than an internal clock. The Hamiltonian of system R is composed of the Hamiltonian of system B, the clock, the Hamiltonian of the rest, S, and some interaction. Now we have to add to this picture the interaction Hamiltonian, the one responsible for the time measurement. So we have the von Neumann Hamiltonian HVN. So we couple the measurement device E to the system whose energy we want to find, and we examine the dynamics. The total Hamiltonian is therefore HT, the sum of all these, and the effective Hamiltonian, once we treat HA as D to DTA, becomes this one. What we see in the Heisenberg picture that Yakir likes much is a time-energy uncertainty relation. So there is a minimal duration for the energy measurement of a system whenever the time comes from an external clock. This is the result. Also of potential interest is the non-hermeticity of the effective Hamiltonian. It turns out that when you measure the energy of a system, you mess up with its time. And when you mess up with its time, you get a non-Hermitian effective Hamiltonian, which leads to a non-unitary evolution in time. So this was one unexpected result. We can also see some different ticking rate between clock A and clock B. This is another manifestation of the non-hermeticity of the effective Hamiltonian. So this was case A, when we couple the system to a measurement device, and the measurement device gets its time from clock A. Now let's see what happens when the measurement device gets its time from clock B. We repeat the same exercise. I skip the details just to show you that eventually there is no time-energy uncertainty relation in this case, but still, interestingly enough, the effective Hamiltonian is very explicitly non-Hermitian. And we still have this open question whether this is a bug or a feature. We don't know, and we wish to find out. And this becomes much more important. So yeah, we answered the open questions about time-energy uncertainty relations, but we got some other open questions. And now this was Yakir's idea. Yakir said, okay, let's examine what happens when I have two systems with two clocks. One of them is accelerating. How would the dynamics look in this case? So again, within the Page-Wouters framework, when time is treated as a dynamical variable of a clock, we took, let me skip to the picture because it's nicer. We saw that when we have two inertial clock systems, then both of which show the same time and the same dynamical evolution. But now, if one of the clocks accelerates, then from its perspective, the dynamics of system B would seem to be non-unitary. And if both systems accelerate, then dynamics would seem non-unitary from each perspective, but it would be different from both perspectives. So Yakir knew that, but we needed to show explicitly the mess, and we did. And the final case that we analyzed was the case of gravitating clocks. So if we have two quantum experiments, one on the moon and one on Earth, and the moon and Earth attract each other, then again the clock is non-inertial, and we see again that the effective evolution from the perspective of a non-inertial clock is non-unitary. And again, the question floats whether this is a general property of quantum gravity maybe, or just a feature of this Page-Wouters model. I'm eager to know. Okay, as I promised, we use these clocks in order to devise dynamical non-locality in time. But the talk has already been condensed, so let me wrap up. These are Yakir's gifts to the world, but there are still some gifts we have to open. And I think that we all live for this purpose. So this is a list of open challenges that I'd like to take, and maybe some of you will too. First, I feel that we have to complete the nice story of Yakir about the Heisenberg-based particle-counterparticle description. There are the fractional cases, which are more challenging. I have a question about dynamical non-locality beyond quantum mechanics, because we discussed Popescu-Rohrlich boxes when Sandu wasn't here, luckily. But you may ask, what is the Popescu-Rohrlich analog of dynamical non-locality? What can be more non-local than the dynamical equation stemming from the Heisenberg picture? I don't know. Yakir is now working on something he once told me in my PhD, quantization of space and time using modular operators. I think this is a nice challenge. Yakir also has a remarkable idea about renormalization based on convex sum of Lagrangians or Hamiltonians. I think Yakir will be glad to tell you about it. I think that this is really fascinating. There is a paper by Yakir, Jeff, and Sandu, Each Instant of Time, New Universe. I think that it could really start a new revolution about time, and we should continue in this path. There is a recurring theme in our discussions these days about self-measurement, self-reference. And fortunately, each day Yakir comes up with another gift, another idea that we can explore. With one promise that Yakir made at the Israeli Academy of Sciences to show us by the end of, by his 100th birthday how to say free will in physics. So we are waiting for this, Yakir. With that, I'll conclude. Thank you, Yakir, for all your gifts and guidance. May you have many more years with landmark contributions to science. I also use this opportunity to say something I didn't say enough. Thank you, Lev, thank you, Avshalom, and thank you, Sandu. We are both brothers, with Yakir as a father, but you were also my fathers. And as the young child, I sometimes rebelled. I tried to find my own way. Not enough. Depends whom you ask. And first, I apologize for this, and I also wish to thank you for helping me to become a better researcher. That's all. Thanks.